Hello everyone, my name is Chuan. Today I'm going to talk about PCF, which is a novel way to do traffic routing and provide performance guarantee under network failures. This work was done with my PhD advisor, Professor Sanjay Rao and Professor Mohit Tawamalani. Let me start with some background. The network performance requirements are increasingly stringent. The traffic is rapidly increasing, and people are expecting better and better experience. Failures which have great impact on network performance are very common in wide area networks. So it is very critical for network architects to design their networks so that the desired traffic can be served over a target set of failures. The network performance of such design typically depends on the mechanism used to respond to failures. In the traditional traffic engineering mechanism, links may be overloaded upon failures. So, many works have been developed to design traffic engineering mechanisms to proactively guarantee that no link is congested on failure, or in other words, the network is congestion-free. These congestion-free routing mechanisms are an important class of traffic engineering schemes. They provide tractable models to deal with large state space of failure scenarios, for example, all F simultaneous link failures, and guarantee a network throughput that can always be served. These mechanisms typically involve lightweight online operations upon failures. Among them, FFC is the state-of-the-art approach and uses tunnel-based forwarding. Provided a set of pre-selected tunnels and traffic demand, FFC computes a reservation on tunnels so that throughput can be guaranteed across failures. However, we found that FFC's mechanism is not flexible enough, and its throughput can be very conservative, especially comparing to the optimal mechanism. Optimal mechanism here refers to the mechanism to recompute the best routing in current scenario upon failures. It has the most flexibility and gives you the best throughput. But it also brings higher response overhead related to online operation, because you will need to solve a linear program each time when a failure occurs, and you will need to update states of routers. It is also intractable to provide performance guarantee under failures, because it needs to enumerate all scenarios in the target failure set. So both of FFC and optimal mechanism have their merits and demerits. To summarize, FFC provides tractable failure analysis, but the throughput that it guarantees is low. The optimal scheme provides the best throughput, but to do tractable failure analysis is hard. Further, the response overhead of FFC is low, whereas the overhead of optimal scheme is high. And our goal is to design a new mechanism which sustains high throughput with low response overhead while providing tractable failure analysis. In our paper, we show that FFC is conservative, and we present the deeper insight of the underlying reasons. In particular, we prove that FFC's performance can be arbitrarily worse than optimal, even with exponentially many tunnels. And FFC's performance can degrade when we provide more tunnels. To address these issues, we propose a set of novel mechanisms called PCF. PCF ensures the network is provably congestion-free under failures, while performing closer to the network's intrinsic capability. Further, our experiments show that PCF schemes can sustain higher throughput than FFC by up to 50% on average across the topologies, while providing a benefit of 2.6 times better in some cases. Now, let's first see an example. This is a network with 5 links. The three links from S to U have capacity of 1/3, and the 2 links from U to T have capacity of 1. And there are totally 6 tunnels L1 to L6 from S to T. Let's consider single link failure. No matter which link fails, at least 2 links in the first side and at least 1 link in the second side are available. So I'm able to send 2/3 unit of traffic from S to T. As mentioned before, in FFC's design, it will need to make reservation on tunnels. For example, FFC can reserve 1/6 on each tunnel. Note that this reservation is constrained by the link capacity. If we increase the reservation on any one of the tunnels here, at least one link will be overloaded. Now, if one of E4 and E5 fails, the reservation on the remaining tunnels can only carry 1/2 unit of traffic. So, under single link failure, the performance guarantee for throughput is only 1/2 for FFC, which is worse than the network's intrinsic capability. Of course, there are other ways to make a reservation on these tunnels. However, we proved in our paper that FFC cannot provide a performance guarantee more than 1/2 in this example, no matter how it makes the reservation. We look into the underlying reasons of why FFC is conservative in this example. And the issue is that FFC's reservations are made at the granularity of entire tunnels. After the reservations are made, they cannot be released when failure occurs. In this example, if E4 fails, tunnels L1, L3, L5 also fail, and the capacity on E1, E2, E3, which is used to make reservation for these tunnels before, cannot be reused for other tunnels in FFC, which causes a waste on link capacity. While in the optimal mechanism, the capacity is still available to be used to route traffic. As a result, FFC provides a more conservative performance guarantee than the optimal mechanism. Our mechanism, on the other hand, can solve this issue and achieves optimum performance in this example. So, how do we do this? We know that FFC doesn't provide enough flexibility in network response. That's why its throughput is conservative. Optimal mechanism, on the other hand, has the most flexibility in routing, but doesn't provide tractable failure analysis. So the key to our solution is to carefully choose the flexibility in network response so that the throughput can be improved while still providing tractable models for failure analysis and avoiding large response overhead. In particular, we introduce an abstraction called logical sequence. A logical sequence is essentially a sequence of nodes. Here, we use the logical sequence SUT, which tells you that the traffic is sent independently in the two segments S to U and U to T. In addition, let's treat each link as a tunnel. On each segment, we want to make a reservation to ensure that it works upon failures. In the SU segment, there are 3 tunnels, and under any single link failure, at least 2/3 unit of capacity can be used. So we can reserve 2/3 in this segment. In the UT segment, there are 2 tunnels, and under any single link failure, at least 1 unit of capacity can be used, so we can reserve 1 unit in this segment. Combining them together, we know that we can reserve 2/3 unit of traffic on the whole sequence. Note that this reservation is always available to be used under any single link failure, so we can guarantee the optimal throughput of 2/3. Now let's see logical sequence more formally. A logical sequence queue from S to T consists of a series of nodes that we refer to as logical hops, and we refer to each consecutive hop as logical segment. Note that unlike physical tunnels, we don't require direct link between a logical segment. In order to use the logical sequence, we need to make a reservation on the sequence, as FFC needs to make the reservation on the physical tunnels. To make a reservation on the sequence is essentially to make a reservation on each logical segment separately. For each segment, PCF allows the reservation to be made through the underlying physical tunnels or other logical sequences connecting this segment. We also consider conditional logical sequence, which is only active under certain conditions. For example, a logical sequence can only be active when a set of link fails. Then this sequence can work as a backup path. Using conditional logical sequence can provide even more flexibility in routing. Next, let me explain how we model a logical sequence in PCF. We wrote a linear program to figure out the reservation on each physical tunnel and each logical sequence so that a maximum throughput can be sustained under up to F link failures. So the objective of this linear program is to maximize the throughput. And the constraints include link capacity constraint, which is to ensure no link capacity will be exceeded for the reservation. And the key constraint is to ensure that for any node pair ST and under any failure scenario of interest, the reservation we make on ST, including physical tunnels and logical sequences, is sufficient to sustain the throughput from S to T and the reservation of other logical sequences which use ST as a segment. Besides the limitation of tunnel reservations, we also found that FFC is conservative in another way, and its performance may degrade with an increase in the number of tunnels. Here is another example topology. Now let's provide 3 tunnels L1 to L3 to FFC. To plan for single link failure, what FFC will do is to pre-compute maximum number of tunnels sharing a common link, which is 1 here. Then it will estimate the number of tunnel failure, which is also 1. So it will consider all 1 tunnel failure. However, if we add the tunnel L4, then L3 and L4 are sharing the same link, which means that killing 1 link may result in 2 tunnel failures. So FFC will plan for all 2 tunnel failures, including failing L1 and L2 at the same time, which will never occur under single link failure, and the performance is very low. Thus, providing more tunnels to FFC may hurt the performance. PCF, on the other hand, can solve this issue by modeling the fact that when 1 link fails, L1 and L2 cannot die at the same time. In our paper, we proved several propositions related to FFC's issues and PCF's solutions. We proved that PCF's performance does not degrade with additional tunnels and performs at least as well as FFC. We also proved that there exists some network. Even if we provide all tunnels to FFC, its performance can be arbitrarily worse than the optimal. But there, PCF's performance can meet the optimal using 1 logical sequence and polynomially many tunnels. Next, I will discuss the implementation of PCF mechanism. We proved that when logical sequences do not recursively depend on each other, a local proportional routing mechanism can be used to implement the model. This also means that these sequences can satisfy a topological order, which we more formally define in the paper. In such cases, we can always redistribute traffic on the active tunnels and logical sequences. This is similar to FFC's implementation of locally distributing on live tunnels. In more general cases, one simple implementation approach is to use a centralized controller. On each failure, the centralized controller can solve a linear system to determine the new routing. And solving a linear system is much easier than solving an optimization problem. Moreover, the linear system we solve is of a special kind, and we believe that in the future, it's possible to do a fully distributed implementation even for the general cases. PCF consists of a family of schemes, and this graph shows these schemes and FFC. PCF-TF is a version which has a fine-grained model of network structure and uses exactly FFC's routing mechanism. It doesn't involve logical sequence, but it is already better than FFC. As you move to the left, when you use logical sequence, the performance gets better. And if you use conditional logical sequence, it gets even better. All these schemes below can be implemented using a fully distributed mechanism, and the schemes on top can be solved using a linear system. In our evaluation, for PCF-LIS, we chose topologically sorted sequences by using shortest path. For PCF-CLIS, we additionally added sequences that are activated on the failure of a link. We select physical tunnels so that they are as disjoint as possible. We evaluate our models on 21 topologies, among which the biggest one have 151 edges. And we use the gravity model to generate traffic metrics. In most of our evaluation, we use demand scale as our metric. That is a factor by which the traffic demand of all pairs can be scaled. We first pick delta-com, which is the largest topology we use, and we use FFC and PCF-TF to design for single link failure with different tunnel options. We can see that using 2 tunnels is best for FFC, and adding more tunnels will hurt the performance, which confirms our observation before. PCF-TF, on the other hand, matches FFC's performance when 2 tunnels are used, and performs better as tunnels are added. We observe similar trends with all topologies and across demands. Since 2 tunnels provide better results for FFC, in the following experiment, we use 2 tunnels results to represent FFC. We next evaluate the performance of our schemes relative to FFC. We report the ratio of the demand scale for a given scheme to the demand scale with FFC, and we consider up to 3 link failures. To avoid disconnecting the topologies, we split the capacity of each link evenly across 2 sublinks that fail independently. The graph here shows the fraction of topologies versus how much better can the optimal scheme achieve over FFC. And you can see that there is a big gap between FFC and optimal. And if we use PCF-TF, which has the same response mechanism as FFC, we can improve over FFC by 11% on average and more than 50% in the best case. If we use PCF-LS, where a fully distributed response mechanism can still be used according to the logical sequences we chose, we can improve over FFC by 25% on average and performs 2.6 times better in the best case. If we use PCF-CLS, we can improve over FFC by 50% on average and matches optimal for most cases. We also evaluate across different demands and use other metrics. And we observed similar trends and improvement over FFC. In addition, we use an interesting heuristic and shows feasibility of achieving nearly optimal performance for most topologies with local routing on the single link failure. We evaluated the solving time of each scheme when designing for multiple simultaneous link failures. For most topologies, the solving time is under 10 seconds. And even for our largest topology with more than 300 links, it took under 100 seconds to solve. On the other hand, for many topologies, the optimal scheme does not finish within 1 hour. And for the largest topology, it took days to finish. In summary, our paper shows that existing congestion-free schemes perform much worse than the network's intrinsic capability, and we uncover the underlying reasons. To improve the performance over existing approach, we propose PCF by carefully introducing flexibility in network response. This allows us to achieve high throughput, tractable failure analysis and low response overhead at the same time. Formal results show that PCF is provably better than FFC, and our experiments show that PCF achieves up to 50% improvement over FFC on average across 21 topologies. And this will be the end of this talk. Thank you for your attention.